split this topic up into two parts. Make sure you've watched the first part first. This is the wordier and algebraic bit. So that's arithmetic sequences, and there's a very closely related topic here which we didn't do at GCSE called arithmetic series. Series is just a sum of terms of a sequence. So if our arithmetic sequence went 3, 5, 7 and 9, i.e. always plusing 2, the series would be 3 plus 5 plus 7 plus 9 and so on. We use Sn for the sum of the first n terms. So in the above example, if I wanted to find S2, I would just be adding the first two terms together. That would be 3 plus 5, that would be 8. If I wanted to find S4, then I would add all four of those terms together. 3 plus 5 plus 7 plus 9, which is going to give me 24, and so on. The formula that we're given, and we are given this in the formula booklet, is that for an arithmetic sequence, if the first term is a, if the difference is n, and if there's n terms, then this sum of n terms, which is written Sn, is equal to n over 2, and then in a bracket we've got 2a plus n minus 1 lots of d. Now I'm going to prove that in a couple of slides turn, but I think it would be better to use that to start with. In fact, we could just look at the sequence that we had before and we can show that it works for, say, S4. We know S4 equals 24. On the sequence that we had, which went 3, 5, 7, 9, we could say that A is equal to 3 because it starts with a 3. We could say that D equals 2 because the difference between 3 and 5 and 7 and 9 is always 2. And if we want to find S4, we're going to say N is 4. So if we plug that all together, we would get 4 over 2 times 2 times 3, and then we've got n minus 1, so 4 minus 1, and d is 2. We could simplify that. 4 over 2 is 2, 2 times 3 is 6, 4 minus 1 is 3, times 2 is 6 as well, so 2 times 6 plus 6, 2 times 12, which gives us 24. So yeah, on a very base level, we got S4 is 24 by just adding them up, and we got it by using the formula. Okay, so we'll leave the formula up there at the top for a little bit, but let's try and apply it to a question that we can't just write out all the terms for and add them up. We want to find the sum of the first 50 terms of 8, 11, 14. That's obviously going up in threes, so we can say that A is 8 because the first term is 8, D is 3 because it's going up in threes, and N is 50 because we want the first 50, the sum of the first 50 terms. That means we're trying to find S50. And if we plug everything into that formula, we'll have 50 over 2, 2 times 8, plus 50 minus 1 lots of 3. Simplify it a little bit, 25 lots of 16 plus 49 times 3, 25 lots of 163, and that'll give us that the sum of the first 50 terms is 4075. Okay, let's look at a slightly more complicated version of that. Again, I've stuck the formula at the top. We want to find the fewest number of terms for this sum to exceed 3000. In other words, we want to find n so that Sn is bigger than 3000. Now, if we look at this sequence, we do know the value of A. We know A is equal to 6 because it starts with a 6. We know D is 8 because it's clearly going up in 8, and N is the thing we don't need to, or we're trying to find, so we don't know. So let's put them into this left-hand side instead of saying Sn. So we can say N over 2. We can say 2 lots of A, so that's 12, plus N minus 1 lots of 8. And we're saying that is bigger than 3000. Now, there's lots of ways you can deal with these brackets. I personally like just doubling both sides to get rid of this N over 2. And I'm also going to simplify the middle. So instead of saying 12 plus n minus 1 lots of 8, that's going to be 8n. And then 12 minus 8, so 8n plus 4. So we've sort of got ourselves towards a quadratic inequality here. And generally with quadratics, what we want to do is make one side equal to 0. So we'll expand that bracket. We'll take away the 6000. And we'll say that's greater than 0. And then you can try to factorize this one, but it's pretty darn horrible. So I much recommend you use your polynomial solver. If you do that, you'll get your two possible values of n. a 19.1, and minus 19.6. Now we still haven't answered the question because it says we want to find the fewest number of terms where that exceeds 3000. Now n has to be positive, so we do know that it's this 19.1 that we care about. You can't have minus 19 terms in a sequence. But if we're solving a quadratic inequality, I would still prefer that you sketch it out and use that to make your judgment. So we've got our positive quadratic. We know it goes through 19.1 and minus 19.6. We want to be greater than 0, so we're interested in these ends. So n is less than minus 19.6, which, as we said, doesn't really matter, or n is greater than 19.1. N does have to be an integer as well. We can't have 19.1 terms in a sequence, so the smallest integer bigger than 19.1 is 20. So our answer for the fewest number of terms to exceed 3000 is 20. Okay, I know it's been fun so far, but get ready. We're going to look at a proof, which is even better. Now, this is one of the only proofs in A-level that you can be asked to just repeat from scratch. So it's well worth making sure this page is copied out correctly and that you've gone through it a couple of times. I've tried to break it down into like wordy steps, but you should make sure you can do this yourself without looking at the video. First thing I'm going to do is I'm just going to rewrite on the top the nth term sequence from before, because we're going to need that. So we're going to try and prove this sum to n formula. We're going to try and prove that we have this n over 2 times whatever. And the first thing I'm going to do is I'm going to write out what that sequence would actually look like. So if I was doing Sn, then I would want to have the first term and the second term and so on and so on, and the n minus 1th term and the nth term. And I'd want to add all of those together. That's what Sn actually means. So instead of writing u1 and u2 and whatever, I'm going to use the formula and plug in what that would tell me. Now, do remember, if we're saying we want to do un, we always have n minus 1 lots of d. So if we've got u1, we're going to have 0d. The first term is just a, which is also what we expect it to be. The second term, we're going to have a plus d. The third term, fourth term, whatever, we don't really care. The n minus 1th term, we're going to have n minus 2 lots of d. And the nth term, we're going to have n minus 1 lots of d. So that's another way we could write out the sum of the first n terms. And I've said here that our next step, our second step, is to reverse the order, and I'm going to do just that. So I'm going to write out still Sn, but instead of writing a on the left-hand side, I'm going to write that on the right-hand side. Instead of writing a plus d on the second term, it's going to be the penultimate term. Middle bit, don't really care about. And then we've got these last two terms here, so a plus n minus 2 lots of d, and a plus n minus 1 lots of d. Really should have given that a little bit more space to breathe, but hopefully you can still see that. Now the second thing we're going to do, or the third thing, sorry, is we're going to add these two steps together. So on the left-hand side, we're going to end up with 2 lots of Sn, and then we're going to be really careful about how we add these together. I'm going to add the a to the a plus n minus 1 lots of d, and that's going to give me 2a plus n minus 1 lots of d. And then going to add the a plus d to the a plus n minus 2 lots of d. That's still going to give me 2a. And I've got 1d over here and n minus 2 lots of d here. That's overall, again, n minus 1 lots of d. Middle bits, who knows? We do the same sum here. So we're still going to end up with 2a plus n minus 1 lots of d. And we do the same sum here. And we're going to end up with 2a plus n minus 1 lots of d. Now, if you think about how many of these we've actually ended up with, we've ended up with n lots of them. We've got the first, the second, the third, the fourth, fifth, all the way up to the n minus 1 nth. So we can put this all together and we can say, we've got n terms here, we can say that this 2Sn is equal to n lots of 2a plus n minus 1 lots of d, and that's very nearly what we actually need. To prove, we just need to divide by the 2, so we'll get that just Sn on its own is n over 2 lots of 2a plus n minus 1 over d. Have a pause, see if you can replicate that proof yourself now. It is quite a nice one. It just involves a very simple trick of reversing an order around, but it's quite powerful in the result that it proves. Okay, so there is actually another version of Sn that I haven't introduced so far to avoid confusion, but it's worth knowing that it exists and how we can prove it's the same thing. So I'm saying that Sn is also equal to n over 2 times a plus l, where l is the last term in the sequence. Now remember that the last term in the sequence of n terms will be the nth term. So L is just another phrase for un here. So we could just as well replace it with an a plus n minus 1d. If we do that, we'll get a plus n minus 1d. And if we just tidy up those two a's together, we'll end up with exactly the same formula that we've been using for the last couple of slides. Now, sometimes this version is easier, sometimes the other version is easier, up to you to choose which is more useful, but I'm going to use this a plus l one for this second example here. So use this, show the sum of the first n odd numbers is n squared. So the first odd number is 1, the nth odd number, so the last term, is 2n minus 1, and our value of n, because we're just looking at n odd numbers, is n. If we plug that into our formula, so we're saying Sn is n over 2 a plus l, then that's going to give us n over 2, 1 plus 2n minus 1, which is going to give us n over 2 times 2n. 2's will cancel, and we'll end up with our sum to n is just n squared. So the last thing that we can do here is we can introduce words, and the A-level questions on arithmetic series are nearly always wordy questions, and the key becomes not really remembering the formulas, although that is important, but pulling out the right information from the question. It's probably worth just quickly writing these down one more time. You do need to start making sure that you learn these. Okay, so reading our question, we've got Jill gives money to a charity over a 20-year period from years 1 to 20 inclusive. She gives 150 in year 1, 160 in year 2, etc., etc. So this forms an arithmetic sequence. We want to find the amount of money she gave in year 10. So the amount of money, not the sum of money, is going to be U10 that we need to find, which means we're going to use our first formula. We know that A is equal to 150 because she gives £150 in year 1. We know D is equal to 10 because it's going up in £10 increments. So if we want to find U10, we just need to do A, so 150 plus n minus 1, so that's 9 times D, so 10. So she gives £240 in year 10. Second question, calculate the total amount of money. So total suggests we're going to do a sum over a 20-year period. So what we're trying to find here is S20, the sum of the first 20 terms. So again, we know A is equal to 150, we know D is equal to 10, and now we know N is equal to 20 as well. So we can put all that together, 20 over 2 times 2A, so that's 300, plus n minus 1, so that's 9, times D, so that's times 10. So we'll end up with 20 over 2 is 10. That bracket times is up to 390, so she's given £3,900. Okay, then we get more words. Kevin is given money to the charity over the same 20-year period. He gives A in year 1, so that's our initial amount, and the amount of money he gives each year increases, arithmetic sequence, with common difference 30, so that's our D. We want to find the total amount of money that Kevin gives, so total amount is Sn, over a 20-year period, so we're talking when n is 20, and we're told this is twice the total amount that Jill gave. So twice the total amount Jill gave would be £7,800, and we want to find the value of A. So putting that all together, we're saying that Kevin's sum over 20 years is equal to twice Jill's sum over 20 years is equal to £7,800. We know that A is just this capital A, we know D is 30, and we know N is 20, so we'll plug them in. S20, we're going to have 20 over 2, we're going to have 2A, we don't know that. N minus 1 is 19, and D is 30, and we know that's equal to 7,800. 20 over 2 usefully simplifies just down to 10, so we've got 10 lots of 2A plus 570 is 7,800. We can then divide both sides by 10, I suppose, or you could expand out the brackets if you wanted. 2A plus 570 is 780. Take away the 570, so 2A is 210. Divide by 2, so A is 105. So he gives £105 in year 1. Okay, so we're going to do 2 more wordy questions. I suggest you pause the video at this stage and have a go at them first yourself. I'm going to write down the formulas first and then we'll crack on. Okay, so this is one of those classic, here's a pattern I've made out of matchsticks. How many matchsticks are we using? We're told there are 4 sticks for the first square and 7 sticks for the second square and so on. So we can get from that that the first term is 4 and that the constant difference is 3 because it's going up in 3s, then goes up to 10. The first question, an expression for the number of sticks required to make an arrangement of n squares in the nth row. This is a UN question because we're looking to find just the amount to make that row. So we can just plug those numbers, A is 4 and D is 3, into our UN formula, and we can say UN is 4 plus n minus 1 lots of 3. Now I would probably tidy this up, and if you do that you'll get that UN is 3n plus 1, but there you go. For part B, this is actually an SN question because it mentions the total number of sticks. Now it says 10 rows, so that will tell you our value of n is 10. And again, all we have to do is plug those numbers into that formula. So for B, we could say S10, the sum of the first 10 terms, 10 over 2, we've got 2A, so A is 4, so 8. This is going to be n minus 1, so this is going to be 9, and D is 3. That'll give us 5 lots of 35, which will tell us we need 175 sticks to make the first 10 patterns. Then we get on to a slightly more complicated question. We say we start with 1,750 sticks, and the mistake that they want you to make here is to look at the 175 you've just got and say, well, just times it by 10. But patterns don't work that way. The amount it doesn't scale linearly. This is an SN question, but it's actually an SK question because we're talking about completing K rows, so the sum of the first K rows, and we're saying that we do have enough sticks to do this. So that must be less than 1,750 because then we'd have enough. We could equally say that S of K plus 1 is greater than 1,750, and I think this same method would work with that. But it's going to be more complicated having a K plus 1 than a K, so I'm going to use this first option. So we do know A is 4 still, we know D is 3, N is K now, so let's sub that into our formula and see what it tells us. It would tell us K over 2, 2A, so 8, plus K minus 1, lots of D, so lots of 3, is less than 1,750. I would then probably tidy this up a little bit, so K over 2, and this would be 3K plus 5 inside the bracket, is less than 1,750, and then maybe double both sides, so K lots of 3K plus 5 is less than 3,500. You can do this in a couple of different ways. You're just trying to get it to a quadratic with everything on one side. So maybe expand this out, 3K squared plus 5K, maybe take away the 3,500, less than 0, and then that looks like it's going to be a pain to factorize, but fortunately they have already factorized it in the question, so we know it's going to be 3K minus 100 and K plus 35. If you were really paranoid, you could actually check that works, but I'm pretty sure it does. Okay, and then for D, all we've got to do, show that. For D, to find the value of k, now this is a quadratic inequality, so you should draw a graph. And the two key values we're going to get are 100 over 3 from the first bracket and minus 35 from the other bracket. So it's a positive quadratic. We know it goes through at 100 over 3, or 33 and a bit, and it goes through minus 35, and we want to know when it's less than 0, so we're interested in this bit below the axis. That means that our value of k must be between minus 35 and, let's put it in a decimal, 33.3. We want the largest value k could be that this would work, so the largest value in that gap is 33. So we can say that k is 33. Remember, we can't have a decimal number of rows. And again, we're just going to look at one more wordy question. Have a go at it yourself. I've actually cut out part A, which was to prove Sn is what it is, so you might want to try that as well, just to make sure you remember it. But again, I'll write down the formulas and then we'll crack on. Okay, so we've got a polygon with 16 sides. That suggests to me that we're going to use n is equal to 16. The lengths of the sides form an arithmetic sequence with a common difference of d, so we're not being told d in this case. The longest side is 6 and the perimeter is 72. Now there's two ways you can go with this one, but if I'm being told the longest side, you could take that as being the last term in the sequence. So we could go ahead and say L is 6 and A is TBD. So let's do that. We'll say L is 6 and A is A. And we'll use the other version of the formula, which is n over 2 A plus L. So putting that all together, we've got S16, the sum of 16 sides, is equal to 16 over 2 A plus 6. And we know that it's equal to 72 centimeters because that's the total of all of the sides of the polygon. So 8 lots of A plus 6 is 72. Divide by 8. A plus 6 equals 9. Take away the 6. A equals 3. So the shorter side of the polygon is 3 centimeters long. Secondly, we're being told to find the value of D. Now, a couple ways we could do this. I suppose if we know that the last term is 6, then we also know that's the 16th term of the sequence. So we could use U16 and say this is equal to A plus 15D. We also know A is equal to 3, so we can say 3 plus 15D. And then we could subtract the 3, so 3 is 15D, divide by 15, so we'll get the common difference there is 0.2 centimeters. And there you go.